Lab 2, Motion of a Falling Object. The goal of our second physics lab was to observe the motion of an object that has dropped from rest and falls straight down. We then wanted to plot our data and compare it to a predicted computational model. Tracker and VPython were used to compare my model versus the predicted computational model to see if my data was accurate. I observed a 0.4 kilogram orange drop from the top of a bed in the negative y direction. Since the sum of the forces acting on the system did not equal zero, the two forces being gravity and air resistance, or drag, we can see from the data, graph, and computational model that the velocity is changing and increasing. In this lab, we use Newton's second law, V final is equal to V initial plus F net over mass times delta t, to see how the forces acting on the system led to a change in final velocity from initial velocity. We also used final position is equal to initial position times average velocity times delta t to find the value for final position. A non-zero net force means that the sum of the forces of an object, the sum of the vector forces, are not zero and the forces are not balanced. This means that velocity will change, it will not be constant, and the object will accelerate. In our example, the two forces acting on the system are gravity and drag. Force of gravity is derived by the equation F is equal to mass times acceleration. In this case, the mass is 1 kilogram and the acceleration is 9.8 meters per second squared, and therefore the force is 9.8 newtons in the downward direction. The force of drag is minus v times velocity squared. V is the drag constant and depends on the object, its speed, and its position. Drag force opposes motion, so in this case it is upward. Tracker was used to follow the position of the orange against the time it fell, recorded in seconds. The orange started from my hand on the top of the bed and fell in the negative y direction to the bottom of the floor. The start time was at 0 seconds and the initial position of the can was at 0 meters. I measured initial velocity from 0 seconds to 0.058 seconds and found it to be negative 78.31 meters per second in the y direction. The time of the last observation was 0.291 seconds, and the final position of the can was negative 0.416 meters in the y direction. To create a computational model, I used VPython. I inputted the initial mass of the orange as 0.4 kilograms and set the initial position and velocity vectors equal to 0. The object started falling at a time of 0 seconds, and the data was collected in increments of 0.001 seconds. In my code, I applied Newton's second law to display a change in final velocity. Again, we can only see this if the sum of the net forces is not equal to 0. In this case, the forces acting on the system were gravity and air resistance, or drag. For the force of gravity, I set the gravitational constant equal to 9.8 and j hat, the unit vector, equal to 0, 1, 0, showing a direction in the y-axis. I set W as the force of gravity equal to minus ball.m, the mass of the orange, times the constant g times j hat. For the force of drag, I figured out the drag constant b by looking at the final position in my computational model and finding a value for b until that value matched that of my experimental value for final position. I set Fc as the force of drag equal to the constant b times the magnitude of the velocity vector squared times j hat. The force of gravity was negative because it was acted upon by the Earth, and the force of drag was positive because it moved against the motion. The equations for ball.vel and ball.pos, the velocity of the orange and the position of the orange, were inputted from Newton's second law to find the final velocity and final position of the orange. From my model, you can see the graph of position versus time. This graph is different from that of constant velocity because from the slope of the position versus time, we can see in the beginning the velocity starts off slow, and as time goes on, it gets faster. The two arrows on the ball represent the forces acting on the orange. The yellow arrow represents the force of gravity, while the blue arrow represents the force of drag. Here is the data from my computational model versus my model from Tracker on Excel. From comparing the graphs, you can see that the experimental data and the computational model do match each other quite well. However, due to the fact that not many data points were collected on Tracker, my trendline was not as accurate as it should have been. Any other discrepancies could have been from not correctly identifying the center of mass in my Tracker video. Terminal velocity means an object stops accelerating because drag force becomes equal to gravitational force. Therefore, the model with drag force will predict an object's terminal velocity. From the graph displayed, Series 1 shows an object that was thrown down, and Series 2 shows an object falling from rest. From this, one can see that if an object is thrown down, it will also reach its terminal velocity. However, it will reach it sooner than if the object was falling from rest. In conclusion, this lab modeled the motion of a falling object through Tracker, and a computational model through VPython was created in order to compare my experimental data versus predicted data. In the end, I was able to prove through Newton's second law that if the sum of the forces is not equal to 0, then the velocity will change.